Welcome to Math 408, L functions and sphere packing. This is lecture 15. And I had originally given people the option of, do you want to do more Fourier analysis or do you want to move on to the applications of sphere packing? And then I realized that I cannot move on to sphere packing without doing at least a little bit of a digression, which is somewhat related to things we need to do related to the topic of the course, the Riemann Zeta function. If I teach Fourier analysis in a class with L functions in the title, and I do not talk about the Riemann Zeta function, when I die, they will not let me into mathematician's heaven. I have the same belief when I teach multivariable calculus if I don't do Green's theorem. There are certain things which just must be done. And so, out of curiosity, how many of you have seen the Riemann Zeta function before? Right, so everyone has seen it, so we'll do this pretty rapidly. Have you seen the functional equation, the analytic continuation of the Riemann Zeta function? Okay, I'm seeing less okay. Have you seen the Poisson summation approach to this? Okay, so one of the things that often happens in mathematics is you have results of different levels. And you have some low-hanging fruit that can be done without too much trouble, and then with a little bit more work, you can get better results. For the Riemann Zeta function, if you want just a little bit of an analytic continuation, it's not that bad. It can be done very elementarily. If you want a more extensive one, then a great way to do it, not the only way, but a great way to do it is through Poisson summation. Given that we have just spent time rigorously proving Poisson summation, let's use it. I remarked that without loss of generality, for most purposes, there's only one function we ever apply the Fourier transform to, and that is the... So what is the function? It's going to be a nice function. It's going to decay rapidly. Its derivatives have to decay rapidly. Standard normal, or its cousin, just any kind of scaled normal. But the normal distribution is going to be the key one. So I'm going to go through the basics of the Riemann Zeta function very rapidly. So zeta of S is defined as the sum n goes from 1 to infinity of 1 over n to the s. And this converges if the real part of s is greater than 1. So this is horribly called a p-series in calculus, where they would use 1 over n to the p. Given that we're about to write this is the same as the product over primes of 1 minus 1 over p to the s inverse, I really don't want to call this a p-series because I want to reserve p for prime. This equation is why we care so much about the Riemann Zeta function. The following is probably the easiest question you will ever be asked in a math class in your Williams career. First one, let's see who's the first one to answer it. What is the next integer after 2020? 2021. Excellent. After 2021? 2022. Yeah, okay. In fact, there is an explicit formula for the nth integer. F of n equals n. We know a tremendous amount about the integers. We actually know about the spacing between adjacent integers. It's always 1. We know how many integers there are up to n. There's n. We have complete knowledge of the integers. The primes are much more mysterious. And there's a lot of terrific quotes about the primes, how they have all this structure, but they also have all this randomness. The idea is by knowing things about the integers, we hope we can pass on that knowledge and deduce things about primes. And the way you prove this equivalence is you use the fundamental theorem of arithmetic. We do not have that many fundamental theorems. If you see the word fundamental, or sometimes it's pronounced central in probability, it's important. What other fundamental theorems do you know? Calculus. Fundamental theorem of calculus. What else? Central limit. Central limit theorem. I will call that the fundamental theorem of probability. What else? Algebra. Fundamental theorem of algebra. What else?
Finitely generate abelian groups.
Do they call that fundamental? It's a good theorem.
First theorem.
I'm sorry?
No, it's a fundamental theorem. I think it's every abelian group is.
Wait, I'm sorry. Do they call that the fundamental theorem of?
Yes.
Okay, then that's another one. And I'm willing to call that a fundamental theorem. Sometimes they talk about the fundamental theorem of linear algebra, about breaking up the dimensions. And to me, it's not quite the same as all of this stuff. But fundamental theorem of arithmetic, any integer can be written uniquely as a product of prime powers if you write them in increasing order. And it's a nice exercise to show that these two are equivalent. What do you think you use to understand this product on the right-hand side? It's something we've seen time and time again, but it's not written in the normal form. I'll write it a little bit differently. So is it clear now that it's geometric series, but was it not clear here? But I'm saying this is something that's really worth thinking about. If when you see this, you think geometric series, you've got to be able to translate that knowledge up to here as well. So as a nice exercise, try to prove rigorously. I'm not going to assign it as homework, but try to prove rigorously the equivalence between the two. There's a tremendous amount you can get once you have this equivalence. One of the things is by knowing how quickly this sum grows, we can get information about how many primes there are. So a lot of these are special values. If we take the limit as s goes to 1 from above of zeta of s, what would that equal? Infinity. Therefore, there exists infinitely many primes. Because if there were only finitely many primes, this product would still be finite as s goes to 1. You can do a lot more. This is not a class in analytic number theory, but if it were, if you looked at the sum up to x, when you take s equals 1, that sum would be about upsized log x. If I want to understand sums of reciprocals of primes, if I take the log of both sides, I would get like log x here. The log of a product is the sum of the logs. The main term is going to be the sum of the reciprocals of the primes. And you can use this to get information that the sums of the reciprocals of the primes diverges. That means the primes are more numerous than the perfect squares. The sum of 1 over n squared converges. The sum of 1 over p diverges. Speaking of, anybody know what zeta of 2 equals?
Pi squared over 6?
Yes.
I thought it was pi over 4.
No. Nope. Pi over 4 is the Gregory-Leibniz formula. When you integrate 1 over 1 plus x squared from 0 to 1, that's pi over 4. This also implies that there are infinitely many primes. And the reason is if you take s equals 2, each of these factors is rational. If there were only finitely many primes, it would be rational. Have I mentioned the worst paper I ever almost wrote in this class?
No.
Okay, so we know that there's infinitely many primes because zeta of 2 is irrational. So this is irrationality. The question is, does it give us any sense of how many primes there are? By looking at s equals 1, we know that the sum of the reciprocals of the primes diverges. That's tremendous information. If you go back to Euclid's proof of the infinitude of primes, is everybody familiar with Euclid? If there were only finitely many, you multiply them all and add 1. Either that's a new prime or it's divisible by a prime not on your list. It gives you a density that's basically greater than or equal to like log of x. And the truth is about x over log x. So what Euclid gives you is nowhere close to the truth. And I was wondering, well, if we use the irrationality of pi squared over 6, we actually know how irrational it is. There's a way to quantify that. Can we use that to get an estimate about how many primes there are up to x? And the first result I got was that the number of primes up to x using this is at least log x. So it's worse than Euclid. However, this is not where the story ends. It's actually much worse because how do we know how irrational this is? Well, if you actually go to the paper that proved it and open it up, you see that at one point they use the prime number theorem. So by assuming that there's x over log x primes up to x, I can prove there's at least log x primes up to x. It was the worst result I had ever proved. I then worked on it with some students, and we were actually in the end able to get a nice result and open up the proof and see, well, where are you using the prime number theorem? Can we remove that? And we ended up getting much better than log x. We actually got almost x over log x infinitely often. But I wanted to mention this just as a warning that when you use a result, always check and see what is the input for that result, what is being used, what is being assumed. And if I'm assuming the prime number theorem to try to prove something weaker than the prime number theorem, this is not good mathematics. I'm sorry?
But you proved it.
Yes, I mean, it is a correct proof, and as an editor of the Journal of Number Theory, I have received papers claiming an elementary proof of Fermat's last theorem, where by assuming Fermat's last theorem, they are able to prove Fermat's last theorem.
Good proof.
I mean, it's a correct proof. If you assume Fermat's last theorem does follow. So this is the basics of the Riemann zeta function. One of the reasons we care so much about it is you have this nice product over primes. If you take the log of that, the log of a product is a sum. We know how to deal with sums. And complex analysis loves logarithmic derivatives. So again, this is not a class that assumes complex, but I know some people are either taking it now or have taken it, so I just wanted to throw that out there. So the first thing is I write annoyingly that this converges if the real part of S is greater than 1. We would like something that converges for every value of S, or if not for every value of S, at least for most values of S. And it turns out you can extend this function so it's well defined everywhere except at S equals 1. And there's a couple of different ways to do this. There's a couple of cheap ways. So the first one is zeta of S is equal to, I want to make sure I get it correct, S over S minus 1 minus S times the integral from 1 to infinity of the fractional part of x times x to the negative s minus 1 dx. And so x is equal to x minus the floor of x. S equals sigma plus it, and sigma is greater than 0. So this new formula works for more values of s than before. You might notice that we're writing s as sigma plus it. We're mixing the Greek alphabet and the standard alphabet. When you prove the Riemann hypothesis, you can tell people how to write things. Until you do, we will follow the original notation. This is what I was told in grad school, and I support that. You want to use the same notation as everybody else. All right, there is another extension. There's the Dirichlet Eta function. It's sometimes called the alternating zeta function. So eta of s is the sum, and goes from 1 to infinity, of negative 1 to the n plus 1 over n to the s. I'm just making sure, yes. Okay. My notes has an n minus 1 rather than an n plus 1 does not really matter, because it's a parity of two difference. And this is converges if the real part of s is greater than 0. Why does this have better convergence than the Riemann zeta function?
You're only taking half as many values, right?
No, because it goes from 1 to infinity.
It's an alternate.
It alternates. So how does the alternation help us?
You have some negatives that cancel out the positives.
Yes, so when you do partial summation, you can split it up into negative 1 to the n plus 1 as one piece and 1 over n to the s as the other. So the alternation helps. With the partial summation. Briefly, when you sum the negative 1 to the n's, that's a bounded sum. It's either 1 or 0. But when you take the Riemann zeta function, if you sum the 1's, that's growing. And that's what leads to better convergence. And it turns out that you can write zeta of s as, I'll do it this way, 1 minus 2 to the 1 minus s times zeta of s is equal to 8 of s. And so this gives us a formula for zeta of s if we know eta of s. We just now multiply by 1 minus 2 to the 1 minus s inverse. So these are some of the standard ways to get continuation of the Riemann zeta function. They work and they push things up to the real part of s greater than 0, but we actually want something that is defined everywhere. Now the other thing is if you take s equals 1, you can see this is going to blow up. When I move this over, yeah, this gives me zeta of s is eta of s over 1 minus 2 to the 1 minus s. And when s equals 1, that's going to blow up. Good, it should blow up because the original Riemann zeta function blows up. Okay. So what I want to do now is I want to come up with a better way to continue the Riemann zeta function that will give me a continuation for all values of s, not just for some values of s. And this is going to be extremely useful in complex analysis, in analytic number theory. Now, we've seen some continuations before. So we've seen, for instance, gamma of s plus 1 is f gamma of s. So this is the functional equation for the gamma function. Functional equation for gamma. And what this tells us is once we know s in a strip of length 1, we know it everywhere. Just because we probably haven't explicitly remarked about this. So gamma of n plus 1 is n factorial. Can somebody tell me what 5 choose 2 is? 5 choose 3, thank you. 10. What is 3 choose 5?
Can you take?
Well, it depends on how you interpret the question. So this gives me an opportunity to bring in my daughter. Hello, Kayla. So she had the following question in her 6th grade math class. And I should have brought in the statement so I have it exactly. In Z not n, closer to, I'm sorry?
I already have doubt she was asked this in her 6th grade.
She may have rephrased it a little bit, because she's actually taking Algebra 1 with 8th graders. And so she brought home a slip of paper that says, in Z naught n, closer to 0 than negative 3. What is the answer?
What's the question?
Negative 1.
What number?
0. 0 is not natural.
So part of it depends on how do you define the natural numbers. So we'll put 0 in the natural numbers today. My daughter said that there were 2 answers, negative 1 and negative 2. And she read this as in Z naught n, closer to 0 than negative 3 is to 0. And so this is where a lot of times it gets interesting as to how do you choose to interpret something. I'm not going to say with things being recorded how I would interpret it, but I think both interpretations are fine. It's now a question on English and semantics. Why am I saying this? When you see 3 choose 5, what are you thinking of?
3 factorial over negative.
So how do we define 5 choose 3? What is the definition of 5 choose 3?
Number of subsets of order 3 of a set of 5 objects.
It's the number of ways to choose 3 objects from 5 when order doesn't matter. It's the number of subsets of size 3 from a set of 5 elements. That's the definition of 5 choose 3. We then have a formula for 5 choose 3. That formula for 5 choose 3 is 5 factorial over 3 factorial 2 factorial. But the definition is it's the number of ways. What does the definition tell us of 3 choose 5?
0.
It's 0. Now, bravely moving onward, what if we say, let's use this formula here? We would get 3 factorial divided by 5 factorial negative 2 factorial. What is negative 2 factorial?
Some kind of infinity.
Some kind of infinity.
Maybe 3 factorial is 0.
Principle of least action. I want to do the least change. I want to keep 3 factorial and 5 factorial as they are. But this is suggesting that a negative integer factorial should be infinity. And if you look at the gamma function, if you look at what happens at the negative integers, it does come out to be infinity. And so there is a nice generalization of this, and that your formula will actually still hold. So it's nice when things are consistent. Okay, so this is the gamma function, which we've seen before. We want to try to do something similar to the Vmon zeta function. We want to come up with an equation that agrees with the standard zeta function when everything is defined, but will work for other values of s. And so the first thing I want the Fourier transform of a Gaussian. So let's let f of x equal e to the negative ax squared. I'm not worrying about the normalization constant. I don't really care about that. I just need to know how things depend on that a. Right? Because if I want to multiply by 1 over square root of 2 pi times something, that's not going to really affect any of the math. It's just a constant factor. This is the meat. So we need to compute f hat of y is the integral from minus infinity to infinity e to the negative ax squared e to the negative 2 pi I xy dx. Now, if we knew complex analysis, we would do a contour integral, we would complete the square and do all of that stuff. But this is not a class with complex analysis. And I believe I gave this just as a problem to think about, not to actually do.
No, I think you gave it.
Oh, did I give it as one to do? Oh, then I gave it to you as one to do. Oh, good. So how did we do this?
You can break apart.
Break
So how do we break it apart?
Cosine of 2 pi I x y.
So we could do cosine plus I sine. But if we try to do cosine plus I sine, the integration is not going to work out. Oh, were you able to get it to work?
I expanded the Taylor series to cosine and then
Oh, okay, sure. Then, yes.
fancy.
Yes. So that's okay. So that's essentially what I was going to do. So yes, the sine part doesn't matter because it's going to be an even function. We have so much decay. I'm not worried about anything. And so we can just write this as cosine of 2 pi xy dx. And then this is minus infinity to infinity, e to the minus ax squared. The sum and goes from 0 to infinity of negative 1 to the n, 2 pi xy to the n, sorry, to the 2n over 2n factorial. Right? And again, I'm not going to bother justifying everything. Everything works because we have so much decay. We will get 2 pi y to the 2n over 2n factorial. And then we'll have the integral from minus infinity to infinity e to the minus ax squared times x to the 2n dx. Yes? How do we handle this?
Induction.
So one way is induction. First, I'm going to send x to, say, 1 over the square root of a times x. And when I do that, I'll get just e to the negative x squared. And then over here, or here, if you want, I'll use a new letter just to avoid confusion. X is 1 over square root of AU, so dx is 1 over square root of A du. And this will become a sum, and it goes from 0 to infinity. Now we'll have a 1 over square root of A to the 2n. So I think we bring in a root A over here. So 2 pi y divided by square root of A to the 2n over 2n factorial. We have a 1 over square root of A. And then we have an integral from minus infinity to infinity of e to the minus x squared x to the 2n dx. Yes? And then this is a question of just how much algebra do you want to do? So this is a 400 level class. What I think I'll do is just show you enough to know that you could do it. And so if you let I of n be the integral minus infinity to infinity e to the minus x squared x to the 2n dx. It's actually interesting that it might actually have been better not to send it to 1 over square root of A times u, but maybe to have a factor of 1/2 over here. It's not going to make a huge difference. It's just going to be where we do the algebra bookkeeping. So you want to integrate by parts. So what do you want u to be? What do you want dv to be? So the hard part is we have an e to the negative x squared. We've got to figure out how we're going to handle the e to the negative x squared. What does it want with it?
2x or 2x.
Yeah, it wants an x or 2x. And now you can see why I might want the 1/2 there. That would just make things a little bit easier. And so if we do it as e to the negative x squared, x dx, we can integrate that. We want a 2 here, a 1/2 here, so we would get a 1/2 e to the negative x squared, I think, with a minus sign. If we had the e to the negative x squared as the u, when we take the derivative, we'll have a derivative of x squared coming down. And that's just going to make things worse. That's going to give us a power of x. And then when we integrate the x to the 2n, we're going to have another power of x that's going to go in the wrong direction. So now we would have an x to the 2n minus 1. We get 2n minus 1 x to the 2n minus 2 dx. And now when you look at the integration by parts, we have, this is going to be uv minus the integral of v du. Well, the uv piece is going to just be 0 because of the huge decay. And so we get in is going to be the negatives reinforced. We get 1/2 integral from minus infinity to infinity e to the negative x squared x to the 2n minus 2 dx, and we pull out a 2n minus 1. Or in is 2n minus 1 over 2 times in minus 1. And so we can just pull all of these off. And so with a little bit of algebra, you can now finish the problem. It turns out that if you want the algebra to be really nice, the integral from minus infinity to infinity of x to the 2n, 1 over square root of 2 pi e to the negative x squared over 2 dx, this is the standard normal, is equal to 2n minus 1 double factorial, which is 2n minus 1, 2n minus 3, 3 times 1. It's just the algebra simplifies nicely. The factors of pi simplify nicely. My goal is not to dot all the I's. My goal is to just give you the broad brushstrokes so it puts it to a point where you can now see what to do. And then you can feed all of this back in. And then algebraic miracles happen. And so I strongly encourage you to go and do things. You will have ratios of double factorials divided by factorials. So let me just show you a little bit of how that algebra will look.
Factorial.
I'm sorry?
Isn't it still just a double factorial?
Well, so let's look at 2n minus 1 double factorial over 2n factorial. This is the same as 2n minus 1 double factorial over 2n minus 1 double factorial 2n double factorial. These cancel nicely. And this is 2 to the n factorial. Because all the terms here are even. So for each term, I pull out a 2. I have 2n, 2n minus 2, 2n minus 4, 2n minus 6. It's 2 times n, 2 times n minus 1, 2 times n minus 2. So this simplifies to 1 over 2 to the n factorial. If you look over here to what I had just erased, and what we just had a moment ago, you will see that this would actually go in very nicely with what we were looking at. And when we had this expansion for the Fourier transform, we put in the cosine, and we only had the even powers surviving. Well, the Fourier transform of the Gaussian, I've been telling you, is a Gaussian. This doesn't look like it's going to be a Gaussian, because we're only having, even powers of n survive. But this cancellation takes all the evens and moves them down to just all integers. So I strongly urge you to go through the calculation in detail. Make sure you can do it. It's a really good calculation to be able to do, but you will get that the Fourier transform of a Gaussian is a Gaussian. If you try to do this in Mathematica, I believe Mathematica can actually handle this without too much trouble. And so if you just do, integrate exponential negative x squared exponential negative 2 pi I xy, x goes from minus infinity to infinity. Yep, and it punches it out perfectly. And if you then make it negative ax squared, it should be able to handle this as well. It might give me some concerns about whether or not a could be positive or negative. Yeah, so as long as the real part of a is greater than 0, Mathematica just plugs out an answer like that. And given that this is the 21st century, you should always test your calculations by going to some program like this and making sure.
Mathematica to be even harder.
I'm sorry?
I think Mathematica is even harder to use than just doing the regular math. It never works with it.
A lot of it is you have to know how to hold its hand. You have to know how to input things properly. But it tells us that if f of x is e to the negative a x squared, then f hat of y is e to the negative pi squared y squared over a square root of pi over square root of a. And so you can see it's still a Gaussian, but what happens is you had an a upstairs in the numerator of the exponent, now it's downstairs. So what this tells you is if one of them has a variance going to infinity, the Fourier transform has a variance going to 0.
Isn't that kind of like the uncertainty?
In fact, it is exactly the uncertainty principle. there's two parts to the uncertainty principle. One part of the uncertainty principle, and if people want, we can have a digression on this, is a statement about a function and its Fourier transform. So there is a theorem that says you cannot simultaneously localize a function and its Fourier transform. What does that mean? If you have a function, you can calculate, the mean value. Let's assume the mean value is 0. And it has some kind of variance. So the greater the variance, the more spread out your function is. Think of these as like a probability distribution. Or maybe it's amplitude squared as a probability distribution. The theorem is that the more localized you make a function, the more spread out its Fourier transform is. The physics content is that for some reason, you can actually associate operators to position and momentum. And that the Fourier transform theorem applies in this case. But the uncertainty principle is a consequence, really, of some beautiful mathematics here involving the Fourier transform. And this is telling us the more we localize over here, the smaller we make A. So as A goes to 0, right, because then this is really the same as dividing by 1 over A, and it's having a variance going to infinity. Okay, any questions about this calculation? So again, if you want to see more details, just let me know, but I'm hoping that this is enough details to get a sense of how you would do it. And we can bypass a lot of the complex analysis by using Taylor series, and then you have to use Fubini's theorem, and you have to justify that we can do the interchanges. And if there's time later today, I'll give you another example where the interchanges fail. And so what I want to do is I want to just briefly sketch the key ideas of how you would use Poisson summation for the Vmon zeta function's functional equation. Just because it's nice to see applications of Poisson summation. It's a very powerful technique. What can we use it for? So the first is we're going to define two functions. Omega of x is the sum and goes from 1 to infinity e to the negative pi n squared x. And theta of x is the sum and goes from minus infinity to infinity e to the negative pi n squared x. And which way do I want to do this? Omega of x is theta of x minus 1 over 2. So the idea is if I understand theta, I understand omega. If I understand omega, I understand theta. And these are nice Gaussians. So how many of you have seen the method of least squares? Okay, so when you have the method of least squares, the x's and the y's are no longer variables in some sense. They're the inputs, they're the data you observe, and the a's and the b's are the variables. Here, don't be thinking really of x as the variable. X is related to the variance of the Gaussian, and it's a negative n squared. It's really a function of n. So with a little bit of work, you can show omega of 1 over x is equal to negative a half minus x to the 1/2 over 2 plus x to the 1/2 omega of x. And this is coming from theta of 1 over x is equal to x to the 1/2 theta of x. And that's from Poisson summation. So if you think about what's going on, if I look at theta of 1 over x, well, Poisson summation says if I sum something over all the integers, it's the same as summing the Fourier transform over all the integers. And so this is my argument here. And so if you want, my function is f sub x of n is e to the negative pi n squared x. So, my sum over all the integers of fx of n should be the same as the sum of all integers of the Fourier transform at n. And each one of these is just a Gaussian. We know what the Fourier transform of each one of those is. So again, the goal is not to go through all of the algebra slowly, but to just give you a sense of what are the ingredients so that you can now do it. We're just using Poisson summation. Which function are we applying it to? This is the function. It's a function of n. If you want, I could define it over here with a t. Makes no difference. And then I'm just saying, by Poisson summation, if I sum this over all n, that's the same as summing over the Fourier transform of all n. And so we just have to compute the Fourier transform of each one of these. That is no longer on the board because we are confined, unfortunately, to just a local screen. But we just calculated what the Fourier transform of this was. And it's going to have x being replaced with 1 over x. That's the role that our a was playing. And so now that we have that and we have this, we have a nice relation between theta at x and theta of 1 over x, or omega of x and omega of 1 over x. How is this useful? Well, it all comes down to a very clever way of starting to write things down. And so we're going to start with the following. I am interested in looking at the gamma function of s over 2, and I want to divide this by n to the s and pi to the s halves. Do we know what the definition of the gamma function is? Yeah, we have a nice integral for it. So I can write this as an integral from 0 to infinity. And now when I put everything in play, it's going to be x to the s halves minus 1 e to the negative n squared pi x dx. And this is just doing a few changes of variables. Right? For the gamma function, I want an e to the negative x, not an e to the negative n squared pi. So what I would do is I would send, x to u over n squared pi. And if I do that, then this is going to become very nice. It'll become just e to the negative u. And over here, I'll still have, s halves minus 1 as the power, but now I'll have a n squared pi, so that will give me an n to the s and a pi to the s halves. I still have this negative 1, but that negative 1 is taken care of by the dx. And one of the reasons why we write the gamma function the way we do is rather than putting the negative 1 there, we can write it as dx over x. This is a much better way to view what's going on, because when you look at dx over x, if I rescale x, if I change variables by scaling by a constant, dx over x is unchanged. And so when I'm doing a rescale like this, it's not going to change the dx over x. It's still going to become a du over u. And so we end up having this piece over here. No independence over here, no independence over here. If we now sum over n, we get pi to the negative s halves, gamma of s halves, zeta of s, because when we sum over all the n, 1 over n to the s, that's just the zeta function. It's the integral from 0 to infinity, x to the s halves minus 1, and now we have a sum from 1 to infinity e to the negative n squared pi x. That's just our omega of x. So we now have an integral representation of the zeta function. Okay. It's not immediately clear why we are happy about this. Well, what do we know about omega or theta? We have nice equations with their values at x to their values at 1 over x. So when you have this integral from 0 to infinity, I claim if we split it up nicely, we can actually use this change of variable x to 1 over x. How should we split up the integral? So the integral from 0 to infinity is the integral from 0 to something plus that something to infinity. And by doing that, in these two over here, there'll be a nice interplay between x and 1 over x. So any thoughts as to, I'm sorry?
To 1?
Yeah, to 1. And so if we make this a 1, then we can take anything from 0 to 1, and by replacing x with 1 over x, we can move it now to 1 to infinity, so both integrals will be over the same region. So algebra, we would get pi to the negative s halves, gamma of s halves, zeta of s, is going to be the integral from 0 to 1, x to the s halves minus 1 omega x dx, plus the integral from 1 to infinity of x to the s halves minus 1 omega of x dx. So now what we do is let's let x be 1 over u. So dx is negative 1 over u squared du, which means, I think that's all I need, okay. And then x goes from 0 to 1, u goes from infinity to 1, right? But because I have this minus sign, that will flip the order of integration to now be from 1 to infinity. And so we'll get that it equals the integral from 1 to infinity of x is now going to be 1 over u. So that's u to the negative 1, so it's going to be u to the 1 minus s halves. I'll have a omega of 1 over u. The dx is going to be a du, but I now have a u squared. So that's a u to the minus 2, so that makes this 1 a negative 1. Right? And then I have the other piece, plus the integral from 1 to infinity x to the s halves minus 1 omega of x dx. And now I can just replace u with x. It's just a dummy variable. This is the integral from 1 to infinity of x to the negative s halves minus 1 omega of 1 over x dx plus the integral from 1 to infinity of x to the s halves minus 1 omega of x dx. But we know how to replace omega of 1 over x in terms of omega of x. That was the Poisson summation that has, oh no, it has not been erased yet, yay! It's still up on the board. So we just plug that in here and we do the algebra. And so when the algebra is all done, you get 1 over s, s minus 1, plus the integral from 1 to infinity of x to the s halves minus 1 plus x to the negative s halves minus a half omega of x dx. And if you look at what omega of x is, omega of x is the sum and goes from 1 to infinity e to the negative pi n squared x. This has exponential decay. We're staying away from 0, so we're going to have terrific decay. This integral is going to converge. And this provides an integral representation. This exists for all values of s other than s equals 0 and 1. Now what's interesting is if you replace s with 1 minus s. So if I replace s with 1 minus s, I get 1 minus s, and I get 1 minus s minus 1 is just negative s. Oh, I have 2 minuses. That's the same as s minus 1. So this piece is unchanged when I replace s with 1 minus s. So just go through and do the algebra. So over here, So this is going to give us, the functional equation. So 1 over s minus 1 is the same as 1 over 1 minus s, 1 minus s minus 1. Yes? Just algebra. The other piece is I have x to the s halves minus 1 plus x to the negative s halves minus a half. And if I replace s with 1 minus s, I get x to the 1 minus s over 2 minus 1 plus x to the negative 1 minus s over 2 minus a half. Well, this is I have a positive a half, a minus a half, so that's going to be x to the negative s halves minus a half. And this I have negative a half becomes negative 1. Negative s becomes x to the s halves minus 1, which is the same as this. And so what this tells us is, if I replace s with 1 minus s, I have the same value. And this gives us the functional equation of zeta. We get pi of negative s halves, gamma of s halves, zeta of s. This is often defined to be like the completed zeta function. And that just equals the completed zeta function at 1 minus s. All right, so we skipped a lot of the nitty-gritty technical details. I don't think anybody minds. It's just a lot of algebra, a lot of just brute force work, just go through. Big picture, it all comes down to Poisson summation. The fact that we can relate values at the function and values at the Fourier transform. And then to make it really useful was we split the integral into 2 parts, and that's an extremely valuable idea. If you can split things like that, we can do something different in each one, and then we combine them. All right. So if people do want to see other stuff on Fourier transforms and applications of Fourier analysis, let me know. There's other things we can talk about. Otherwise, we can go straight to the applications to sphere packing. But I just could not avoid talking about applications of Poisson summation to the functional equation of the Vmon zeta function, because this is one of the best applications we have with Poisson summation. And you always want to ask yourself, how deep is the result? What do we need to prove it? I will end with, there is an elementary proof of the prime number theorem. People initially thought this was not possible, that you would have to use complex analysis to prove the prime number theorem, which bothered people because we're counting integers. Why do we need to go to the complex plane to count integers? And so eventually 2 conjectures emerged. There is no elementary proof, and if an elementary proof is found, boy, will it indicate better understanding of what's happening. Both conjectures are false. There is an elementary proof. Elementary doesn't mean easy, it just means does not use complex analysis, but it doesn't give us a better understanding of what's going on. Not surprisingly, it gives us much worse results.